So yeah, welcome, Atta, and please go ahead and yeah, look forward to hearing what you've got to say.
Good morning, everyone. It's a great pleasure to be able to discuss the recent paper that, as mentioned, just came out in Methods in Ecology and Evolution. So that is this ecological graph theory. And first of all, I have to acknowledge sorry, I have to acknowledge the work that has been done was funded by Max Planck Society and also partly using the research computing data core in the University of Houston. And also I had very constructive discussion with Professor Azevedo in Houston. And I also have to thank the MEE team for organizing this workshop to be able to explore what this method is. So I'm going to discuss uh, this method in two parts. So the first part is a quick introduction to what it is, and then the second part is actually more of a hands-on demonstration of how it works with the uh, associated codes that are available on the GitHub repository. So the a starting point for this method is that the way I think about the various methodologies that you can use to simulate evolution and ecology. I mean, you can extend it to broader modeling frameworks, but the idea is that in general terms, you can think of any sort of model for a biological phenomenon to be positioned in a three-dimensional space with one axis representing generality, meaning to what extent it is applicable to various different clades and species versus a model that is very specifically tailored to a given species. With respect to complexity, which is, I'm just using it in terms of algorithmic complexity, is like how big or small is the code that specifies that model, and then also stochasticity, meaning that to what extent that framework can incorporate various sources of chance events in biological models, being it either chance events in general or a specific variation in trait values that you want to study. Now, in traditional methods, a lot of them actually are very general, and they are not really that complex with respect to the code required to specify them, and they actually mostly rely on very deterministic frameworks. So your classic Lotka-Volta competition model uh, would uh, would be like that. And I have actually been mostly focused on phenotypic plasticity, but in order to model that over the years, I have actually looked at various types of modeling frameworks, and I tried to really explore the space of possible models in that respect. So using more deterministic models in some cases and using more complex agent-based models where you can have a lot of complexity and you can have a lot of stochasticity. However, they are actually generally very specific to a given species that you're studying. So the ecological graph theory came from the notion that I needed something that would fill in this gap where there would be a modeling framework that is general enough, and it is complex, but not too complex, so it can be explored more broadly, and also it has the ability to incorporate a stochasticity. Now, graphs in ecology, of course, not really a novel idea. They have been used extensively for many years, so you have very different versions of graphs, for example, so individual-based networks, or species-based or clade-based networks. You can also have like one of the more extensively explored areas are food webs, historically been explored in ecological context, and there you have network representation of interactions with respect to the resource usage. You can have the various types of networks where, for example, in this case, a bipartite network, where it is really specifying interactions. So here, for example, pollinators and plants. And more recently, you had the idea of multi-layer networks, which are just much more complex representation of ecological data. Now, what I wanted to do was to look at a way to simulate competition in a graph. And then naturally, when you think of competition, you would think of evolutionary graph theory, which is a highly developed area where you have basically an evolutionary process. So the famous Moran process, which actually simulates the population dynamics by coupling the reproduction and death processes in a way that you can have discrete events in the model instead of the Wright-Fisher model where you have non-overlapping generations. In Moran process, you have discrete reproduction and death events, and that would actually make it naturally lends itself to being transposed into a graph. So you can think of, you can transpose the individuals, represent them as nodes on a graph, and then simulate the birth death process on the graph itself. So, and that was the idea behind the evolutionary graph theory. And so, understandably, you can actually have many ways of doing this because question arises: okay, so do you want to have the death happening proportional to or inversely proportional to fitness, and birth being random, or the other way around? Or you want to have a more complex algorithm? And so people have actually developed extensive literature on that topic. And so I'm not going to go too much into the game theoretical framework, but there's actually extensive literature available. For example, a relatively recent work, a book by Mark Broom and John Rishtash actually explores extensively the current body of literature on evolutionary graph theory. Now, for the most part, the evolutionary graph theory, although it's a kind of generalization, so there are many exceptions, and people have done pretty amazing works on this topic. But broadly, you can think of most of the works done within the framework of looking at what is generally referred to as amplifiers and suppressors of selection. So here, the idea being that what type of a structure of a population, specified by the topology of the network, would promote or hinder the fixation of a beneficial mutation. Now, what I wanted to do, so to move from the evolutionary graph theory to the ecological framework, was really to change the question. So instead of asking what is the selection, or what is the effect of structure, population structure, and selection itself, my question was, what is the conditions that enable coexistence? So that immediately becomes an ecological question. And coexistence here means the presence of multiple species in an ecological community. And so that is actually a huge part of ecological research, just understanding what are the factors. And so you can look at many different resources on that topic, so from mechanistic perspectives. And the idea of the theories developed to understand community, and to a certain extent, more recently, meta-community ecology. So the idea of communities that are themselves structured relative to other communities and connected with dispersal. So then how would you ask the question of coexistence within a graph framework? So I thought if the first step would be to look at the classic model. So the Lotka-Voltra model, in this case, a two-species model, you can actually break it down into discrete steps. And you have to break it down into discrete steps if you want to actually simulate it stochastically. So for example, you can make it into a stochastic Lotka-Voltra model. So that's actually been explored in the paper associated with this workshop. And there you can actually turn the Lotka-Voltra competition model in reactions, and reactions becoming a birth reaction and a death reaction. And so that actually conceptually makes it much easier to then transpose it onto a graph. So what this ecological graph theory would do is just trying to have a Lotka-Volter model in a structured population. And so for that, you can actually come up with an update algorithm. So this is a very simple, and this is not the only possible way to think of a sort of update algorithm in this context, but this is the most, this is the easiest to mimic the Lotka-Volter update or the intrinsic Lotka-Volter algorithm itself. And here is to have a connectivity-based depth. So this is actually for a given individual, A of a species I, the probability of death is proportional to, so this expression Ni plus alpha ij. So alpha ij simply means that the effect of a species J on a species I, multiply it by Nj and divided by Nt. So this just purely what it means is that depending on the competition parameter, so the alpha, the death probability is really a function of the identity of nodes. So each node here representing an individual connected to a given node, right? So then what is the composition of the neighborhood, which, or the species composition of the neighborhood for a given node? And that determines what would be the probability of that node dying, or the individual on that node dying and making that node available. And so once the death happens and you have an empty node, a birth is actually in this case would be a random birth, which fills in the space that has become available. Now, to make it actually more clear, I have to introduce the idea of the temperature of a node. So this is actually used extensively in evolutionary graph theory, where you have the sum of all weights leading to a node as the temperature, and that is actually for a weighted and a directed graph. So that is the most common way to simulate in evolutionary graph theory. However, in this case, in this ecological graph theory framework, I'm actually using undirected graphs, and where the edges, the connections, they have really no weight. However, you have the parameters, the species competition that would specify how species interact. So if you for this type of graph, the temperature is really equivalent to, for a given node, is number of connections or the number of degrees that node has. So how many neighbors are connected to it. So a hot node would have many neighbors connected to it, and a cold node would have very few. And in this case, in a complete graph, so that is a graph where all the possible edges are created between the nodes. Here, everyone is equally hot. So everyone is connected to everyone else. And conceptually, as a side note, the complete graph where you have everyone interacting with everyone else would have an equivalent dynamic to the classic Lotka-Volter model. Because even in the Lotka-Volter model, you really don't have any structure. And actually, so in the paper, we show that is the case. So the complete graph really mimics the behavior that you would expect from the Lotka-Volter model. But on the right side, you see a random graph. And a random graph, since you have not all the possible edges are realized, you have variance in the temperature of nodes. So you have some nodes that are very hot, so they have there are many connections, and you have nodes that are very cold. The connectivity-based death probability, as defined in the ecological graph theory, is not merely a function of the temperature of a node itself, but the composition. To make it more clear, so in this case, here is a random graph where you have two different species distributed across the graph. So again, each node is representing an individual belonging to either of the species. For this given graph, you have a distribution of the temperature for each node, representing how well connected that node is. But for death probability, you use that temperature for any node and then take into account the composition of the nodes connected. So what are the neighbors, and that represent the death probability. Now, so this is a very simple idea. What it means is that you can actually have several things incorporated in this type of model to study the coexistence. So the easiest one is that it's an individual-based model. So you have individuals associated, or individuals belonging to different species in a given community. So you can have a variance in various traits. So the competition parameter can itself be can be coming from a given distribution for a given species. You can have growth rates that would also be variable, or different attributes that you would want to include. So that's just really just a baseline, a vanilla version of what you would want. And then on top of that, you can add various attributes to it. And more importantly, I think specifically because I come from a background where I study the phenotypic plasticity in nematodes, and so these organisms, they do move around. The idea of a structured population in a static form is not really that appealing, but what this framework enables is that you can have the topology of the network changing as well, representing some form of movement. So just to make it, so for example, here is just a network, a random network where the edges are changing over time, and I will explain the various ways that you can implement that. So this is just a random so-called rewiring, and on the right side you're seeing the abundance of the blue species on the network. And so depending on the type of algorithm that you would use for the change in topology during the competition, you would get very different results. And I think that those would be of interest whenever you think of biological or the ecological competition in a space where it is not really about plants, but about animals and things that move around. So for the second part, after this introduction, I will go to a hands-on, just to really clearly show what the model is doing. So the hands-on section, you can actually find all the codes and the notebooks associated with this workshop on this GitHub repository. So you can just download it and play around with it to see how it works. So I think now I can go to this. Hopefully you're seeing. So that's a notebook that is available on the GitHub repository. And so it's the graph methods, which collects all the methods that are used in ecological graph theory as described in the manuscript. So the easiest, in the paper, I illustrate the idea of competition using, at the beginning, using more pedagogical graphs, meaning that there are graphs that are not really biologically realistic necessarily, but they actually show the idea behind this type of competition in a space. So the first one of these is a dodecahedron. So I actually use the dodecahedron, and these are in this section is static graphs. What I mean by that is that the topology of the graph itself is not changing during competition. So in this case, I'm just using a Schlegel diagram to superimpose a dodecahedron onto a two-dimensional space, so a 3D object onto a two-dimensional space. And so this one is using the so SC, meaning a species competition, and dodecahedron graph function. And you can actually give it a number of generations and a species competition. So so that is the alpha parameter. How do these different species affect each other's death probabilities? And so, for example, in this case, if I simulate this, So you can see the dodecahedron has actually no variance in temperature. So you have 20 nodes, and then all of them actually have very low temperature relatively. And then this one started from a random initial composition of 50-50, and then you see the final composition. So this one is actually, this is just such a tiny graph, uh, and there's no variance in temperature itself. So you usually just get a competitive exclusion. So and actually uh, uh, it would be better to describe it as ecological drift, meaning that you can either of the two species are equally likely to become monodominant in the competition because it's just such a tiny space, and there you would expect ecological drift to be dominant. The other pedagogical graph is a King's graph. So King's graph is just so this is the image from this chesschivalry.com, where so the King's graph is just a graph representation of all the possible moves a king can make on a chess board. And so here you can actually you have several parameters. So the n10 is just the size of the board, so it's 10 by 10, and then the probability one would make it as a King's graph. But if you reduce the probability, some of these possible moves disappear, so you have more of a sparse representation of a King's graph. And so here, for example, we can simulate it. So in this case, I simulated about 10,000 steps, probably a bit longer than expected, although this one, okay, so that is done. So in a King's graph, as you can see, you actually have very interesting, so, and that is what I mean by pedagogical representations, because a King's graph, biologically, it is not really that realistic, because as you can see, the temperature has a very interesting pattern, but way too regular for a biological system. But in this case, you have the initial composition and final composition, and a King's graph actually is pretty interesting in the way it behaves, which illustrates how the competition would work. But these are more extreme. Uh, on the GitHub repository, you can use the SC on comp graph, so there's species competition on complete graph. So here you specify the number of nodes. So in this case, we have possible 50 individuals in the community itself, and the time series, and then the species competition case. And in this case, so the complete graph would actually behave basically like a Lotka-Voltron model. So in this case, so as you can see, the graph temperature, so everyone is very hot because every node is connected to every other node. And then this is a random initial composition and the final composition. So in this case, it used the species composition parameter 0.5. So and the 0.5 in the classic Lotka-Voltron model would really promote coexistence because you actually positively affect the survival of the competing species. So it's really actually better to have diversity in this community, given how it is better to have neighbors that are not, they don't belong to your own species. So that in the classic Lotka-Voltron, it is predicted to promote coexistence. And in the ecological graph version of it as well, it would just behave exactly like that. Now, more interesting graphs, of course, you have the Erdős-Rényi graph. So in the ecological graph theory code, that is simulated using the SC on ER graph function. You actually can have Erdős-Rényi graph defined in two different ways or constructed in two different ways. So you can have n nodes that are connected with L randomly placed lengths, or you can have each pair of nodes connected with probability P. So in this implementation, I'm using the latter version. So you can give it the probability of edge creation, and then it would just generate a topology. So here, for example, we can simulate, so this is SC on ER graph with 10 individuals, so 10 nodes with probability of 10% of an edge being created between any two pairs of nodes, and with these species competition parameters. And in this case, so that is a random uh, topology with variance in temperature, a random initial composition, and as you can see, the final composition. The other function, so the other method that is used in this in ecological graph theory, so you can use the small word graph. So I'm actually using the Newman-Watts-Strogatz version of it. So you can have the number of nodes in a graph, the probability of adding shortcuts, and the initial degree of each graph. So this small word ones, of course, is going back to Stanley Milgram, the idea of having a bunch of shortcuts in a network. And so here in this case, I have, any sort of a small word version can be used. And here, for example, this is this is a randomly generated small word graph with a random, so it's variance in graph temperature and then the initial and final composition. And so the more extreme case of this is actually you can use a ring graph. So it's a small word graph with a probability of 0. So there's no shortcuts, and K2, so everyone has two neighbors. And this one is actually interesting as well, but it's probably not ecologically necessarily relevant. Now, the interesting part that in this case is that the idea of having graphs with topologies that would change over time, of course, that is not necessarily a novel idea, but in the context of the ecological graph theory, you can use that in order to change the topology in a way that would mimic a given biological process. So in this case, for example, we have the temporal graphs. We can have many different ways of rewiring during the competition. So in the manuscript, I actually looked at a bunch of very obvious algorithms that you can think of to rewire the topology during competition. So we have uniform rewiring. So M edges are randomly rewired at each step. So it doesn't really depend on the identity of the species. It just purely changes the edges. There's the rich gets richer rewiring. So there's actually inspired by the preferential attachment, specifically the Barbashi-Albert model. So a new edge is formed between random chosen nodes proportional to the degrees. So then the higher, the more the more degrees you have, the more likely you have to get new edges. The poor gets rich, which is the contrast. So it would actually prefer, so whenever it is trying to rewire edges in a given network, it would prefer to attach it to a node that has fewer connections. And then, so these are, I actually gave it some biological examples which would be relevant to these two different methods. You can also have the what I call aggregator methods. So here is that the species would just prefer to be linked to a conspecific. So it is not really based on the degree anymore. So the rewiring method is not based on the degree, but it is based on the preference of the species to be connected to conspecific individuals. And then the repulsive rewiring, so the idea is that the species they prefer to be attached to the allospecific. So in this case, you can actually say in the tools available associated with this model, you can actually do it in a way that one species just has no preference and just randomly attaches to others, and the other species prefers to be attached to nodes that are of that belong to other species. This case is basically, you can think of it as like inter-guild predation, predator-prey ideas in that sort of rewiring. So here actually is from the paper a a schematic representation of how each rewiring works. So on the um, left side, I'm using the dodecahedron, so the 2D representation of dodecahedron, just for simplicity, because it's just such a visually nice graph. But on the right side, you're looking at in random graphs that started from an Erdős-Rényi which was created by Erdős-Rényi method, so with the method that I described, where you have a probability of creating edges between two random nodes, and then the rewiring algorithm is applied to the graph while the competition is happening. So again, the competition and the change in topology, they are happening at the same time. So in a stepwise process, you have the birth death events happening, so the connectivity based death, and then the random birth, and then you have the rewiring steps, and then you keep doing it. So for example, in the uniform rewiring, you have just everyone is equally likely to receive a new edge. So any edge can be destroyed, and if you destroy m edges, you just create m random edges again, excluding the edges that already. So the algorithm, the way it's implemented is just there would be m new edges, so not to repeat what already existed. In the rich gets richer algorithm, as you can see here, you would have more likelihood to receive a new edge if you have more connections, right? So if you have one neighbor, you are less likely to receive a connection than you have two neighbors. If actually if you have noticed in these dodecahedron graphs, so these are dodecahedron graphs where some of the edges I just randomly destroyed simply because in the original dodecahedron, you actually basically have no variance in degree distribution, but by just removing some of the edges that are shown as these thin gray lines, these are where the edges existed when I created the dodecahedron, and then they were removed just to make it to have some variance in the degree distribution, and then I applied the rewiring algorithm. Specifically because in the case of rich gets richer or poor gets rich, it depends on it's conditional on having some variance in degree distribution. So the rich gets richer, so that is C. The more connections you have, the more connections you get, and actually that really reduces the variance in degree distribution, while the mean remains the same. The poor gets richer actually is the opposite way, right? And then the aggregator rewiring, you would just prefer to attach to nodes that belong to your own species, and then repulsive is the opposite. Now, in the code associated with it, this is actually so we have a method called a species competition on Erdős-Rényi graph with uniform rewiring algorithm. So this one, it starts from a Erdős-Rényi with a given probability. So that is the probability for the initial topology, and then a parameter m, which is a number of rewired edges per step, and then you can give it the species competition. So in this case, we can actually simulate it as a relatively quick, and then we can get as you can see, so you have initial temperature and the final temperature. So as you can see, the rewiring method works, and then you can see also the initial and the final composition in the code. So then you can actually basically, in this notebook, you can use any sorts of parameter for the erosion in the initial topology, and then play around with the m. So as you increase the m, you actually make it more close to a complete graph, basically, because you're just making it more likely for everyone to interact with everyone else over time, which is interesting on its own. The rich gets richer algorithm is done with this method. I actually call it it's got a species competition on Erdős-Rényi graph with preferential attachment rewiring algorithm. So in this case, you give it, again, it starts from Erdős-Rényi, you give it the number of rewiring events per step, And you can give it, if you set this parameter RR rewire, so rich gets richer rewire as true, it would just do it as a rich gets richer. And so we can simulate that as also very quick simulation. And as you can see, so in this case, you actually get something that's very expected is that in this graph you can get some of the nodes that are end up being not connected. So then in a node that is not connected, the way the model is treating it is that the parent is just reproduces and the offspring replaces the parent. So then in that case, this kind of uh, rich gets richer algorithm just makes the likelihood of coexistence very high because it just really makes a lot of nodes disconnected from the rest of the network. In the poor gets richer, it's the same function that is used, so the preferential attachment rewiring with the RR rewire set at false. And this one, again, this case is very quick, and it would just create, so you can see the initial temperature and the final temperature, and then the composition that is changing over time. With the aggregator, you can actually use so this one is called a species competition on illustrating with aggregator or repulsive rewiring. So in this case, we have n, which is the size of the network, so the number of nodes, the probability of edge creation for the initial Erdős-Rényi topology, the time, so the number of steps that it is going to simulate, the number of wiring events, the alpha, which is the species competition parameter, and then the preference. So preference is purely how much more likely you are to prefer to attach to the other species. So in this case, for example, for any given species, we have a dictionary. So this species A, we have a dictionary with two keys. So in this case, A would attach to A 4 times more, or it's 4 times more likely to attach to A than to attach to B. And the other, so it's also the other species is also preferring to aggregate with its own. So B is 4 times more likely to attach to another B node than an A node. So in this case, we can actually look at how it does work. It's also very quick. I have to say it is using the network X for the network creation component of it. As you can see, this one has, so you can see the initial temperature, the final temperature of the graph, and the initial composition starting from randomly assigned individuals belonging to either two species to the final composition. And then the repulsive, of course, using the aggregate algorithm, but now the preference dictionary is now set with the opposite idea. Again, you can see that you can actually do it any other way. For example, you can set one species to have no preference whatsoever, so just randomly attaching, while the other species actually prefers to attach to either members of the same species or the other species. So that really depends on what types of change in the population structure you want to simulate with respect to a given biological system. So in this case, we have the same idea of the initial and the final temperature and the final composition. Now, this just was a very brief show of the method available. As you can see, what it is actually trying to do is really expand on the classic Lotka-Volter model, but transposing it into a structured population and enabling both the structure of the population being static to be defined by certain methods of creating the topology and looking at how that structure influences the competitive outcome, and enabling simulations where you have the topology itself changing given some rules, where we can see how the competition or the probability of coexistence changes. And in the paper associated with this, it's mainly in comparison with the Lotka-Voltra model, so just a two-species case, trying to see if the two-species case corresponds to a certain types of graphs, and what types of graphs would deviate from it, what types of graphs would actually promote coexistence or hinder it, and at the same time looking at the rewiring algorithms to see if the changes over time would promote or hinder coexistence. It's just at this point it is just a general method, but what I think uh, is useful is that it can be used to look at the specific cases where you think there's variation in the way the species interact, and also you have a specific questions with respect to how the structure of the population might change over time to see, okay, what is the expectation? Because generally, the Lotka-Voltra model and other models where the population is well mixed, they generally produce results that might not be as relevant as real cases where the actual population is structured in space. And at the same time, this method can be used for a meta community level. So you can actually, using this code, have different communities specified as graphs connected to each other, and then look at how that would affect the coexistence, and depending on the type of questions that you want to ask. So I'm hoping that given the extensive documentations available on the GitHub repository and the paper itself, it could be used to ask various questions in the context of coexistence and competition in a structured population. All right, thank you so much. So if there's any question, I would be more than happy to take.
Awesome. Thanks. That's so cool. I can see there being lots of really interesting uses for that. I have a question just to start off, to give people a chance to just type their questions into the box. And we can also let you, if you are struggling with the typing, you could just put your hand up and you can unmute yourself. But I guess my first question was, that's all really cool and quite it looks reasonably user friendly. So if you were starting a new project, like what would be your advice to somebody who's new to this area? Like where should they start with applying this kind of graph theory?
So I would actually look at it from the perspective that if you are interested in what is broadly known as the coexistence theory, and so there are many tools that are analytical tools that would predict what happens in a basically huge population with no structure. But what you are looking at is a specifically cases. So I have to say for me the initial idea or the initial reason why I looked at this was I look at nematodes or that are associated with insects. And so usually in those cases, you have populations that are very small, and the population size is not very large, but also they are moving and they are in a structured population in a sense that they are over an insect and eventually they actually spread out to the areas around it. So that was the problem, was that I was trying to understand why or how phenotypic plasticity in that case would affect coexistence, where initially, when we looked at that from a deterministic perspective, and that was one of the early works I had done, it was not really the way the model would predict was just so different from what we had observed. So I think in that context, it is really specifically about, okay, what is my question with respect to the organism that I'm either working on or interested? And in that case, how does the structure of the population can be transposed onto a graph? Because that's simply the idea is that, and that is why in this paper it goes through so many different versions of the graph, because it is not really about a specific organism. It is the idea that, okay, there's the possibility of using this kind of competition framework on a different type of structures, really the question is what type of structure I should use for my given organism of interest. So I think that was a very long answer to the question, but I think just to make it more concise, it is the idea that this would be very useful if you have very specific question about an organism or a type of a structure population, and and the traditional methods of local ultra models would not really apply. And I think someone in the chat had asked about the two species, and it's an individual based model, so you can have as many species as you want. Of course, I mean that becomes a trade-off with respect to the size of this network. I think
Yeah,
that was also the idea that you can simply add as many species because, of course, uh, it's not a deterministic model. It's not based on differential equations. So it can accept and it can accept various values for different individuals in the same belonging to the same species, which again, a benefit with that respect.
yeah. So just to confirm for anybody who's watching this later and can't see the chat, the question was just, can the alpha have more than two species, and does it have to add to one?
Yes, and also it doesn't need to add to one because it's just purely represents how they would interact with each other. So it's really can have the same value for everyone. So it's not a really probability insofar as it is a parameter that would mediate or define the way that different species compete with each other.
Yeah,
Uh,
so really flexible then. Yeah. The other question that we've got so far, and if anybody has questions, do feel free to either put your hand up or pop them in the chat. So the question is it possible to consider changes in population size, specifically aggregated population size?
so that's a great question. I have to say that so I'm actually this version of the model because it was um, initially inspired by evolutionary graph theory. It has certain limitations that is that is actually inherited from that framework, and one of them is that in that framework, really, the node is the individual. So the space is not really anything that can exist without the individual. So you can have the birth and death. You immediately just fill in the space. And so in that framework, and the one that I describe in this manuscript is really not. Uh, it's a fixed population size in that respect. However, I think I'm actually working on it right now to have an extended version of this where both you decouple the space from the individual because and that is the reasoning behind it is that from the ecological perspective, some of the most interesting ecological scenarios they involve colonization, where you have an empty space and you would fill in the space. And so those relate to some of the most interesting questions about how does the various factors in competition and chance events affect the final composition of the community that emerges following a succession event, let's say, right? And in that case, what you need is for a space to exist decoupled from the individuals. And it turns out if you change the model in that way, you can actually change it in a way that you can have actually even a stage of structured populations. Because once you break that coupling between individual and a space, then actually your hands are much you can actually basically make it much more complex with respect to ecological interactions that you want to simulate. So right now, no the population size, but uh, I think in the follow-up to that, it would be solved so that you can have variable population sizes over time with
Cool.
no problem.
Nice. So another follow-up from the earlier question about alpha. So how do you decide on the value of alpha? So, for example, would A equals 1, B equals 1, C equals 1 be the same as A equals 0.33, B equals 0.33, C equals 0.33? And how would it be different if you chose something like A equals 1, B equals 1, but C equals 1.5?
That's a great question. So in the way it works, I think that could be a bit slightly misleading, is that broadly, the way you would think about it is that if you have alpha less than one, any value, you are going to have, as a species, you are going to have a more positive influence on the survival of the other species. So if I have a alpha value less than one, I would actually help the other species survive better because I'm just if I'm affecting the death probability such that it is less likely for the other species to die in this kind of very abstract competition model. When it is one, I have no so it's basically it's they usually describe as a neutral case. But any values that are equal, that's basically it is if they are both equally have the same value, especially with the case of one, they have basically no effect on each other. If you have one that is higher, so you have negative effect on the other species. So you have I have an alpha of two, and the other species has alpha of one. Or so worse would be the other species has an alpha that is below one. So that species has a positive effect on my survival. I have a negative effect on its survival. So then you can see what is happening. So usually in the classic Lotka-Volterra model, you have the alpha less than one as being the coexistence condition, where both species would promote each other's survival. The alpha equals one would be the neutral case. So you have basically ecological drift, meaning that either of, so you never have coexistence in long term. You always have monodominance, but the winner is not really determined. So it's just pure chance which one would win. And then when you go to one species having higher than one alpha value, then you have monodominant communities, also not coexistence, but you have the species with the higher alpha as the winner of the competition. So in the paper itself, we actually do that with exploring with different combinations of alpha specifically to correspond to these different types of interactions, either positive or negative between the species or neutral.
Cool. That's very cool. And yeah, that so the response is just thank you so much. That makes a lot of sense and it sounds really good. But yeah, no, I'm sitting here thinking about ways I can use it and some paleo stuff I've been playing around with competition. So yeah, it should be could be some interesting ways of using this method. Does anyone else have a question that they wanted to say out loud or obviously, if you're typing something, um maybe just send me a message so we don't cut you off. Questions? Anything else you wanted to add, Atta, that you felt like you
Actually, just to clarify I can actually show this okay, from the paper itself. The okay, if I may just share this, I think that would clarify the issue. So here actually is that is from the manuscript. So that is the figure one. And so this one, so that is what that was when I was briefly mentioned a stochastic Lotka-Volterra model. So this just basically turns the Lotka-Volterra into a chemical system of chemical reactions. And so you see that it will just simulate it and has a stochastic. So then on the part C, there is this 3 by 3 square where each of the tiniest squares, they represent a number of simulations. So each pixel is the result of a simulation, where the color indicates what was the end point of the simulation, where blue means the species one wins and red is the species two wins, and the purple is coexistence. And then if you look at it, there's the different combination of alpha is used, where you have the alpha 0.5 for both the species. And that is where you basically have all the outcomes are coexistence. So I mean, in this case, because it's a random simulation, you had one case where it was not coexistence, but that is just par for the course. And then, as you can see, whenever you have alpha 1.5, so 1 or 1.5 for a species, that is species with the higher alpha wins in all the competitions. In the right in the middle of this square, you have a case where both of them have alpha equals 1. So that was the random case where you have almost half and half. There's like half of them, half the times species one wins and the other half is species two. And then you can see it just symmetrically changes as you move to, you keep one species at the same alpha, but increase the alpha of the other species and just make it much more likely for that species to win. So that is the general idea with respect to the alpha parameter in the classic Lotkov-Volterra model. So hopefully that visual representation helps with the notion that how does it work? And this is just to make sure this is the result of the classic Lotkov-Volterra model. So just done as a stochastic simulation to show the baseline of what you expect in a population where everyone interacts with everyone else.
Great. Yep. Well, I think we're done with questions. But thank you so much for presenting for us today. That was really interesting, and I think a lot of people seem like they're quite excited to get playing with the method and checking. So don't forget to check out the paper as well if you haven't read the paper yet. And this video will be up online in a couple of weeks once we've had time to edit it and stick that on. And we'll also send you all a copy of that so you can watch it back. And of course, it'll be available on our website. So yeah, thank you very much, and hopefully see people at the next one of these MEE lives.
It was a pleasure. Thank you for organizing this workshop.
No worries.